Hi, here in lecture 34b we are finally at the point where we're going to look at Fourier series through inner products. We'll start by looking at what are called Fourier polynomials mostly in this lecture, hint at what Fourier series are, and also introduce the idea of a partial differential equation, a very brief introduction, getting into more details in future lecture Bs, 35b, 36b, and 37b, though we are going to keep it real basic, okay? You can get into a lot of depth about partial differential equations, PDEs, and make it very tough. We want to keep it basics. We want to understand the basics. The most famous partial differential equations are what we'll look at. They're called the heat equation, the wave equation, and Laplace's equation. All right. So we need to start by talking first about Fourier polynomials. It's easiest to think about it initially on an interval of length 2 pi, either 0 to 2 pi or negative pi to positive pi. I'm going to choose negative pi to positive pi because it's going to sort of fit well with my examples here in this lecture. So some theory first, then we are going to get definitely into examples here. Consider this inner product space. We've seen this kind of thing before. C negative pi to pi represents, as a set, the collection of all real valued functions that are continuous on the entire interval from negative pi to pi. The C means continuous. This is a vector space. You can add functions like this and get another function like that. You can multiply them by scalars. It's also an inner product space. You can define the inner product using an integral. The integral in defining an inner product like this is analogous to a summation that we use for doing dot products. When we're talking vectors in Rn, say V and W in Rn with n components, V dot W, we've seen in the past, is a summation, a finite sum. I goes from 1 to n of the corresponding components Vi and Wi. It would be V1 times W1 plus V2 times W2 plus V3 times W3, etc. In the end, the last term would be Vn times Wn. Functions, I've talked about, can be thought of as vectors because they satisfy the vector space axioms. But you also could sort of think of them as infinite dimensional vectors, one component, so to speak, for each value of t. F of t, as t varies continuously, gives you, you might even imagine, a vertical vector that's infinite dimensional, though that can be misleading because it makes you think the collection of outputs is what's called countably infinite when it's actually uncountably infinite. But if we don't worry about that, and if you don't know what that means, don't worry about it. You can kind of imagine it as being a vector where each component is an output. G of t, vector for g. Each component is an output. You multiply them just like we multiply the components here. You cannot use a summation because we'd be summing an uncountable summation which would not converge, so you have to use an integral. But an integral is an analog of summation. Okay? The corresponding norm of the metric, as I've talked about, is first of all the norm of f would be the square root of the inner product of f with itself, which in terms of an integral would be this. You can also square this and get rid of the square roots if you like. That might be useful sometimes. The corresponding metric, distance function, that gives you the distance between any two functions in this inner product space with respect to this inner product. By the way, this inner product is not unique. You can define other inner products. Is the square root of the integral of f of t minus g of t quantity squared. We are interested in often making this distance small, which means this integral would need to be small, which means the area under the graph of this non-negative function would have to be small. I'm not saying what small means, but you get the idea intuitively. If you graphed f of t minus g of t quantity squared, and if the graph, which would never be negative, is just slightly above the horizontal t-axis, the area under it will be small. And the distance between these functions would be small. The distance between their individual graphs would be relatively small overall. That's an important kind of intuition. For a fixed positive integer n, the following is an orthogonal set in V with respect to this given inner product. With respect to some other inner product, it might not be. Because again, inner products can be defined in lots of ways. We might not get an orthogonal set here, but with respect to this one, we do. This is a set with 2n plus 1 elements in it, 2n plus 1 functions. 1, the constant function 1, cos t, cos 2t, cos 3t, etc. through cos nt, sine t, sine 2t, etc. through sine nt. 2n plus 1 functions. This is an orthogonal set, and therefore it would be a basis for the subspace that spans a 2n plus 1 dimensional subspace of V, which is an infinite dimensional space. How would you confirm it's an orthogonal set? You'd have to do a bunch of integrals. For example, you want to use trig identities here. There's a trig identity that says cos mt times cos nt is this. And that could help you integrate this product, because it's easier to think about integrating these. I mean, you could also perhaps do it with a substitution. Well, the m and n could be different, so that could get tricky. This is the best way to integrate it. When m and n are distinct, so that you're not dividing by 0, this is the result. The inner product of sine mt with cos nt, when m and n are different, is this integral, which gives me this, and here's the key place where I need the fact that m and n are different so that I'm not dividing by 0. You've got to treat the case where m and n are the same separately, but it can be done. You can still use this equation, in fact. It's easier when m and n are equal. This is sine of 0, which is 0. I didn't do that case, but it can be done. You get 0 here because m and n are integers. You end up canceling. Okay, so when you plug in pi and negative pi, the even nature of the cosine function you should check ends up making things cancel. All right, so that was an orthogonal set. What's next? Well, we should verify other facts. Similarly, when m and n are distinct, you get zeros here and here as well. It is important that when m and n are not distinct, when they're the same, these two things are actually non-zero. That's related to the norms of the functions. Furthermore, when you take the inner product of these things with 1, and m is a positive integer, you're going to get 0 as well. The integral of the products of these things is 0. The area under the graph when the graph is above the axis plus the opposite of the area above the graph when the graph is below the axis, everything cancels to give you 0. It doesn't mean the graphs are perpendicular. It means when you multiply the functions, you sort of even out the positive and negative contributions to the integral. That's what it means to be orthogonal in this case. Like I said before, this set of functions being orthogonal would be linearly independent and be an orthogonal basis for the following finite dimensional subspace. W sub n equals that. Notice the word span is in here. Of the infinite dimensional vector space V. This is a finite set, a finite basis, 2n plus 1 elements. When I put the word span there, I mean the set of all linear combinations of those, which is definitely an infinite set. Because the coefficients, the weights, can be any real numbers. It is a subspace, being a span, and it's finite dimensional. V itself is infinite dimensional. There's no finite basis for C of negative pi to pi. There's no finite collection, at least. It's an infinite dimensional space. Given an arbitrary function f in V, we are interested in finding its orthogonal projection, f hat. Though I put a subscript n to match the n there. So for a given positive integer n, f hat sub n is going to be in Wn. I could pick different n's though, so I could get different answers. I'm interested in maybe f1 hat and f2 hat and f3 hat in W1, then W2, then W3. Think of n as fixed though. By the best approximation theorem, this orthogonal projection will be the unique element function in Wn that is closest to f, in the sense that this distance is minimized over Wn. If you consider other functions in place of fn hat in this formula, you're going to get bigger answers for the distance. In other words, geometrically, the area under the graph of f minus fn quantity squared is as small as possible compared to areas under the graphs of f of t minus g of t squared as g varies over wn. You can think of it graphically. It's nice to be able to do that. We are minimizing a sum of squares. The integral is like a sum. In fact, this is sometimes called least squares. This does have finite dimensional analogs, which we haven't taken the time to talk about, though I've hinted at, especially to statistics. Least squares, regression lines. This is related to that. It's not the exact same thing, but it's similar. Slide 3. By the orthogonal decomposition theorem, I can write a formula for this projection function, fn hat. You just saw it there. Big linear combination of 1 cos t, 2t, cos 3t through cos nt, sine 2t, sine 3t through sine nt. This linear combination. These coefficients, these weights that you see are numbers. These are the things that came from the orthogonal decomposition theorem. Ratios of inner products. So I can compute fn hat. I can find it. Just got to do all these calculations. Be good to use technology, and I'm going to show you at Mathematica. I programmed Mathematica to help me do these calculations, though it didn't turn out quite as ideal as I was hoping. But I'll show you what I did when we get to the end. It's pretty cool. You'll want to wait to the end where I show you Mathematica. Since, for example, the inner product of 1 with itself is this integral, which is 2 pi, and the integral of cos nt with itself, now the m and n are the same, I'm just calling it n, is this, which turns out to equal pi. How would you verify that? Use a trigonometric identity. The one to use is cos squared nt would be 1/2 plus 1/2 cos 2nt. That would be easier to integrate, and the part that gives you the non-zero part is the 1/2. If you integrate 1/2 from negative pi to pi, you get pi. The other part gives you 0. The inner product of sine nt with itself is also pi. And because of these facts, this formula for fn hat is often written in a different form, and now I'm going to put the of t's in there. It's often written as this, and this is called the nth degree Fourier polynomial. It is an orthogonal projection of f onto the subspace Wn. This nth degree and polynomial are kind of not the best words, perhaps, because this is not really a polynomial in the usual sense. It's not, powers of t, positive powers of t. So calling it a polynomial is a bit of a misnomer. It's not the best name, but we're stuck with it. It's not an nth degree in the usual sense of nth degree for polynomials either. It's that the coefficient of t in both the cosine and sine is largest when k equals n. Where one of these a's and b's. AK is this formula for k equals 0 through n. And bk is this formula for k equals 1 through n. That's not a typo. This one does go 0 through n, that one does go 1 through n. Got to divide a0 by 2 because the inner product of 1 with itself is 2 pi. This is really the inner product of, when k is 0, cosine of 0 is 1. This is the 1 over pi times the integral of f of t dt. That's the inner product of f with 1. That's the integral, and the 1 on the bottom there is really 2 pi. I only got a pi there to make this formula work no matter what k is, 0 through n. But then I need to adjust for the fact that I get a 2 pi down there by putting a 2 there. Might be confusing. Think about it. You'll see it works. These integrals are related to these inner products, and the pi's are as well. Many people, when they teach Fourier series, they don't talk about inner products at all. They just say, hey, these integrals turn out to be 0 sometimes, and these other integrals are non-zero, and we can define these a's and b's in this way, and this is called the nth degree Fourier polynomial. And they never talk about inner products at all. Is that a good idea? I think it's better to take the inner product approach, as you might guess. For one thing, it unifies the linear algebra to other topics that we've done. For another thing, maybe one's cosines and sines, one cosines and some sines, maybe that's not always the best thing to use for your orthogonal basis. Maybe we should use something different. By the way, notice I didn't call them an orthonormal basis either. By dividing by these other things, I could normalize, but I'm not choosing to make an orthonormal basis. But maybe there's other functions that are orthogonal bases. Maybe they have nothing to do with cosines and sines at all. In fact, that is the case in many applications. If you're interested, look up the word wavelets online, Google it, or look for YouTube videos on wavelets, and you'll find out about other kinds of inner product spaces and other kinds of orthogonal sets where these formulas still work. But it's not Fourier series. Still useful, just not Fourier series. Here's a couple graphs that I made with Mathematica. One where f of t is t, another where f of t is t squared. I'm going to show you the Mathematica at the end here, and you will want to hang on for that. The red graphs are Fourier polynomials of a certain degree that's not specified. They are approximating the blue graphs when t is between negative pi and pi. Negative pi, right about there. Positive pi, right about there. Negative pi, right about here. This one's doing a better job overall, though near negative pi it's not doing so hot. I guess that's not doing so hot either. Pi's right about here. Not necessarily drawing it perfectly. I'm approximating non-periodic functions with periodic functions. I mean, the fact that they involve sums of cosines and sines means the graphs have to be periodic. It's not clear whether this is a good idea or not. It's kind of cool to look at. It's working well between negative pi and pi, because that was my domain for the functions I was thinking about and for the inner product formula. I could pick some other interval besides negative pi to pi, like 0 to 2 pi, or even some other arbitrary interval, like 1 to 7 or something. Wouldn't be so handy to use cosines and sines, though, if the interval was 1 to 7. The area between these curves, and in fact the squared areas, thinking of those as positive areas, the integral of f minus f hat quantity squared is going to be small in both cases. You get a small amount of area between these, except when you get near negative pi and pi, then it gets a bit bigger. But still, overall, you are minimizing the squared area of those things. Here it's sort of a contribution of positive and negative areas, but you'd have to square the difference to get non-negative areas to think about the integral. It's cool, not clear if it's useful. These are Fourier polynomials. What about Fourier series? This lecture is going to be shorter than lecture A was. I'm going to wrap this up pretty quickly. So the intuitive idea so far is that Fn hat will be the unique element of Wn that best approximates f itself in terms of minimizing the total area under the graph of the square of the difference of the functions. A mouthful which you can write symbolically pretty easily. When we were thinking about the previous slides, we were thinking of n as fixed, but I could choose different n's, and I'd get different Fn hats then, if I do. And maybe it's hopeful that if we increase the value of n, to get bigger and bigger finite-dimensional subspaces Wn, that the Fourier polynomial at approximate f would get better and better at approximating it. The distance between f and Fn hat would get smaller and smaller as n increases. it's natural to wonder what happens in the limit as n goes to infinity. Then we get a Fourier series, an infinite sum. You've learned about infinite sums before. You should have in Calculus 2, Taylor series, for example, power series in general. If we're going to understand this, though, we have to make sense of the following ideas. What is the meaning of this kind of infinite sum? Notice the infinity here. What is the meaning of that? Did you pay attention in Calculus 2 when you're learning about power series and Taylor series? The meaning should have been talked about by your teacher there, too. Brief synopsis. You have to think about this kind of expression when you've got a finite n for any fixed value of t as having a limit as n goes to infinity for that fixed value of t. And different t's will produce different limits. The limiting values are a new function. F hat of t, no n here for the subscript. A Fourier series related to f itself. What is the meaning of the infinite sum, though? Also, is such a sum an infinite sum even in V? And if it is it the element in this subspace of V that evidently is an infinite dimensional subspace because it's got an infinite basis? Notice there's no cos nt and sin nt, the dot dot dots go on forever. Is it the element of that subspace that's closest to F? These are tricky here. Actually, this thing is not necessarily continuous. It's actually not necessarily continuous. So it's not necessarily in here. It is for many examples, just not in general. And yeah, what would it mean to have an infinite basis? And is there an orthogonal decomposition theorem with infinite bases? Okay, that's a question we're going to leave unanswered at the moment. Here's our last slide. How is this related to partial differential equations, PDEs for short? ODEs means ordinary differential equation involving ordinary derivative. PDE means partial differential equation involving partial derivatives, still of an unknown function that we'd like to find. We'd like to find the unknown function. There's a special class of PDEs that we're going to restrict ourselves to called linear PDEs. Linear algebra, again. Linear operators, again. Linear transformations on function spaces. And therefore, because they're linear, that's handy because it means sums of solutions are still solutions. Physicists often call such sums superpositions. And that'll be very appropriate in the wave equation case. You're adding a bunch of waves to get a superimposed wave or superposition wave or something like that. This is very handy to build complicated solutions from simpler solutions. So we want to start thinking about the simpler ones, but we want to build complicated ones for a given situation using the simpler ones. The examples we can look at are the most famous. They are the heat equation, which is that, the wave equation, which is this, and Laplace equation, which is this. These are the most famous partial differential equations. They are the simplest ones that have significant applications, at least. First ones thought about, I think. The heat equation does describe heat propagation over time along, well, in the one-dimensional case, along a thin bar of metal, you might imagine, a wire. U is the temperature at any point, T is time, X is a position along the wire. And I think I might have a sign error in here actually. Du dt, the second derivative is often positive. I think this might be a negative sign here. I need to double check that. It might be a negative sign. I'll put a note at the bottom of the video whether there should be a negative sign here or not. If there's one there, there'd be one here as well. Partial derivative notation, subscripts here mean partial derivatives as well, so it's just a shorthand notation for partial derivatives. First order derivative with respect to t, second order derivative with respect to x. Wave equation looks like this. Laplace equation looks like this, and it's traditional not to have t's in there, instead to use x's and y's. T is time in these two equations. X and y are not time in this equation. Though Laplace's equation can describe something that stays steady state over time, but there's no t explicitly in the equation. Here's our final comment, a couple comments. The initial data, initial conditions at t equals 0 in the first two cases, heat and wave, is often represented not by numbers, not by finite number of numbers, but an arbitrary continuous function, f of x, which you could think of as an infinite list of numbers, uncountably infinite, like I mentioned before. You might have an initial heat distribution for the heat equation, or an initial position for a vibrating spring for the wave equation. Not a vibrating spring, a vibrating string is what I meant to say. Representing f, this function f of x at the initial data with a Fourier series will help us solve the PDE. And it's even more in depth than that. The Fourier series themselves will in fact help us solve the PDEs using something called separation of variables, which is not the same separation of variables from chapter 1 of the Blanchard-Devanian-Hall book. It has a slightly similar flavor, but it's not exactly the same. Let's end by looking at Mathematica. You can use Mathematica to compute your inner products. I'm defining inner product of f and g. This is my name here, inner product, of two input functions as that integral. I can compute, for example, if f of t is 1, the inner product of f with itself, we should get what? 2 pi. I can compute the inner product of cosine of n of t with itself and sine of n of t with itself. Mathematica doesn't know n is an integer here, so the answers are pretty weird looking, though they do simplify because n is an integer. Sine of 2 and pi would be 0. These terms would go away when n is an integer. You'd just be left with pi's. For f of t equals t, I can compute my Fourier coefficients. My an's when f of t is t are all 0, in fact. There's no cosine terms in f hat when f of t is t, which is an odd function, and cosine is an even function. The bn's do exist, but are complicated looking, though remember n is a positive integer here, so these do simplify. And in fact, if you plug in, well, I don't want to do b of 0. You plug in b of 1, b of 2, b of 3, etc., you're going to get these numbers. I tried programming f hat in this way, and it was fine as far as finding formulas. There's f hat 8, Fourier polynomial of degree 8, approximating the function t between negative pi and pi. And you could evaluate values there, but it wouldn't graph it for some reason. I don't know why. So what I did was I defined it with summations that I just typed in instead of using the inner product. And this did allow me to make animations with manipulate to see as n increases that the graph of higher degree Taylor Fourier polynomials approximates f of t better and better over the interval from negative pi to pi. Here's the case where f of t is t squared. Now the a's are non-zero, but the b's are 0 because now t squared is an even function. So the sine terms should not be there because sine is odd. Once again, this approach didn't work, so I used another approach using this. And we can once again see these approaching the graph of t squared and the approximation getting better and better as n increases. Okay? So there's our introduction to Fourier series and partial differential equations using inner products, using inner product spaces, more abstract linear algebra. Thanks for watching.